everyone. We're going to get started. This is Dawn Marshall from the University of Iowa. This is our a webinar in the Safer Sim series. Safer Sim is a university transportation center that consists of a consortium of sites. One of those sites is the University of Massachusetts-Amherst. And today, researchers from UMass are going to present a study called Impact of Deflection Angle on Roundabout Driver Behavior. I'm going to hand it over to you guys.
Thanks, Don. Welcome, everybody. Appreciate you taking the time to be with us here today. Our speaker today is Akshaey Sabhanayagam. He's works right now with Green International, a consulting firm here in Massachusetts, actually, and everywhere. But Akshaey is an alumni of our program, and the work that he's going to present today was part of his thesis and also part of a bigger Safer Sim project that we're excited to share the results with today. So without further ado, I'll turn the floor over to Akshaey.
Thank you, Dr. Mahmood. So I'm going to begin with the background of my research. So roundabouts are more popular in Europe and Australia than in America. During the early 90s, the traffic circles and rotaries created traffic congestions, delays, and safety concerns. The negative experiences through traffic circles and rotaries could be an important reason for the lack of interest in roundabouts. So this circular intersection is a typical example of a rotary. The vehicles circulating the central island have to yield to the vehicles entering the approach. Weaving around circulatory roadway is encouraged. Central island diameter is higher in comparison to the modern roundabouts. Entry speed is higher in rotary, that is average around 25 miles per lap, which is comparatively low, where it is comparatively low in a modern roundabout. Due to these reasons, vehicles clog circulated roadway and the rotary fail to fulfill its purposes. In 1966, the British redesigned the modern roundabout and made it into a much safer intersection. On contrary to the rotary, the vehicles entering the approach had to yield to the circulating traffic. When this was laid in an experiment, the results exceeded the expectations. The yield at entry eliminated locking up of vehicles, capacity increased by 10%, vehicles delay dropped by 40%, injury crashes were reduced by 40%. Further ahead, weaving inside the circulated roadway is cut down, reducing central island diameter, allow the vehicles to enter and exit the intersections fast. Entry speed of the vehicles entering the approach was reduced to 25 miles per hour from 45 miles per hour. As a result, the British found that the capacity increased by 10%, vehicle delay dropped by 40%, and injury crash by 40%. In Australia, the researchers suggested that the crashes reduced by 65%. In the recent past, the modern roundabout has started gaining popularity in the US. As you see in this figure, Florida has got the most number of roundabouts, which is somewhere around 1,283, and this statistics was taken in the year 2014. Similarly, a driver is likely to pass through a roundabout once every 363 intersections in Maryland, whereas in South Dakota, a driver has to pass through an average of 22,806 intersections to come across a roundabout. So, advantages of a modern roundabout. When operating within their capacity, the roundabouts typically have lower overall delay than a signalized and always stop control intersections. Less delay means more traffic flow. Reducing idling time and vehicle delay leads to less pollutant emission, and it is environmentally beneficial. The central and split island make the roundabout attractive. The standard signalized intersection has over 32 vehicle conflict points and 24 pedestrian conflict points, whereas the roundabout has only 8 conflict points for both vehicles and pedestrians. Severe incapacitating injuries and fatalities are more rare with modern roundabouts. Numerous studies by Federal Highway Administration and Insurance Institute of Highway Safety has shown significant safety improvements at intersections converted from conventional forms to roundabouts. The study showed overall reductions of 36% in total crashes and 75% in injury crashes and 100% reduction in fatality. In spite of all these advantages, the roundabout faces few challenges like lane confusion, pedestrian crossing, and visually impaired pedestrians. The aforementioned disadvantages can be countered by gradually reducing the speed of the vehicles as it enters the approach, increasing the line of sight of the driver while the vehicles enter the approach. So, so we introduced chicanes to support our hypothesis. So chicanes are S-shaped curves with deflection angles which will limit the speed and improve the line of sight of the vehicles between drivers and pedestrians. And this is achieved by speed reduction by changing geometrical design rather than relying on traffic control devices. So this figure is a pictorial representation of what we did in our model. Like the yellow dot represents the pedestrians, the arrow represents line of sight, and so as the vehicle enters an approach, the line of sight of the blue car is towards the pedestrian, and as the vehicle enters into the second loop of the approach, the line of sight is towards the vehicles in the center island. So this makes this makes it advantageous for the driver as the vehicle enters the approach, where the driver has better line of sight as the vehicle enters the approach. So the hypothesis of the project is to investigate if there is a uniform reduction of speed when vehicles enter the chicane, analyze if the speed decreases when there is an increase in deflection angle. So this was the methodology of a study. The selected site was in Amherst. Data was collected in both AIM and PM peakers were collected. The roundabout was then drafted into AutoCAD, and we used AIMSUN. We used AIMSUN in this analysis. So the trajectory analysis was done in SSA. The site selected is to the north of the campus. It is functionally classified as an urban character. That is, the Eastman Lane is functionally classified as an urban character, and the remaining three approaches classified as an urban minor arterial. The intersection falls under large urbanized area. The roundabout is located to the north of UMass-Amherst campus, so most of the commuters at intersection are associated with the campus. Hence, morning peaker, evening peaker falls between 7 a.m. to 9:30 a.m. and 3 p.m. to 5 p.m. And most of the commuters enter and exit the campus. The camera was set up with yellow dots, where the arrow showed the line of sight of the cameras. So the data was collected on a Tuesday. Data was collected between 7:15 a.m. to 9:30 p.m. on a morning and between 3 p.m. to 5 p.m. in the evening. There were a total of 1,667 vehicles which entered and exited the roundabout during this analysis. The PM peaker had more number of vehicles than the AM peaker, hence it was used for the microsimulation analysis. During the PM peaker, most of the vehicles entered the GRC approach from the south, which exited the Governor's Ave, which is to the west, east. So the deflection angle was increased with respect to the central line of the approach, entering and exiting the roundabout. This impacted the radius of the curvature of the approach. the more the radius of the curvature of the approach varied between 138 feet to 152 feet, and this was because as we increase the radius of the approach, the angle of the length and the angle of the curve increased. So this was the reason for the increase in the increase in radius of the curvature. The base model is the existing roundabout in Amherst. The three revised models were uh, the deflection angle of the approach was increased with reference to the central line. The three revised models were 30 degree. The center angle was increased by 30 degrees, 45 degrees, and later by 60 degrees. So we began modeling the model in MISSIN. So in MISSIN, we were not able to see the changes as the vehicles we were not able to see the changes in speed when the vehicle at the turning movements. And in AIMSUN there was when the vehicles transition from states when a vehicle transitions from a straight path into a horizontal curvature, the driver tends to reduce the vehicle speed. And simulating this in MISSIN, the vehicles were not found to be reducing their speed, and hence changing the deflection angle did not reduce the speed of the vehicle in MISSIN. Whereas in AIMSUN, it was found that the vehicles tend to reduce their speed due to the increased deflection angle feature of roundabout. When the deflection angle was increased, the yield distance to the approach increased. The AIMSUN model automatically calculated the yield distance as the vehicle entered the approach with respect to the deflection angle. This graph represents the mean speed of all the vehicles as they enter the approach. Speed is plotted in y-axis, and the four legs of roundabouts varying deflection angle is plotted against x-axis. This was a preliminary result of analysis. The result significantly proved the mean average of all the vehicles decreases with the increase in deflection angle. So for all the three wise models, the sections were split into three equidistant into three distances. The length of the section increases with the increase in deflection angle. A total of 16,770 vehicles and approximately 6 million data points were gathered. So, this is a plot of all the trajectories. All the data points were plotted in this graph. The location of each vehicle is recorded every 2 seconds. A total of 10 simulation runs were separated based on a unique ID, hence each vehicle has a separated based on unique ID. At this stage, a path for each vehicle was identified. Since the radius of the approach varied in three models, the mean speed of each vehicle was calculated for each of the three ranges of distances. Distance range was plotted in x-axis and speed on y-axis. Likewise, so this graph was plotted for one approach, and likewise we had graphs plotted for all the four approaches. So in this graph, it's clearly seen that based on in the existing roundabout, as the vehicles exited, as the vehicles enter the approach, they continue to go along the same speed till the central island. Whereas in the first model, when the deflection angle was increased by 30 degrees, there was a decrease in speed as the vehicles enters the central island, and gradually, like for a 45 degree, when the deflection angle was increased by 45 degrees, the vehicles tend to go at a much lesser speed, as the speed of the average, the speed of the vehicles was somewhere around 10 miles per hour as they enter the separated roadway, whereas when the deflection angle was increased by 60 degrees, the entry speed was reduced, was almost around 8 miles per hour. So the trajectory files came as an output from AIMSUN and were uploaded to SSAM. SSAM will account for a crash if the vehicle trajectory follows any of the following conditions. The number of conflicts, that is, the number of conflicts is under 1.5 seconds. That is under 1.5 seconds time to time collision on each link. The type of the conflict is defined by the angle of impact, where for a random collision, the angle of impact was set less than 30 degrees. For a lane change collision, angle of it was set less than it was set in between 30 to 80 degrees, and for crossing, it was set more than 80 degrees. So this was a result from the trajectory file. The trajectory files came as an output from AIMSUN. In the result, the result clearly shows that there are no the 30 degree model. There are no crossing crashes, and there are less number of crashes in the 30 degree model in comparison to the 45 degree and 60 degree west. The results indicate that the increase in deflection angle reduces the speed of the vehicle. Hence, vehicles enter at a much lesser speed as we increase the deflection angle. The roundabout with deflection angle 30 degrees tends to have a fewer number of crashes than the existing roundabout. So, analyzing the environmental effect of chicanes with additions in the roundabout would be testing these roundabout scenarios in a driving simulator and comparing the results between a microsimulation model and driving simulator model. Developing a mathematical model to estimate an optimal deflection angle based on entry speed of vehicle would be a good direction after this research. Thank you.
All right, thank you, Akshay. I don't know if you have time for any questions or not. I was hoping, Akshay, you might just talk a little bit more about some of the future studies in terms of the immediate next steps in terms of starting to see some of these designs in practice and recording speeds in the field, or what you think an immediate next step is. Just in terms of what you see as an immediate next step, in terms of if you were to see somebody pick up where you left off, what might be a most advantageous approach. So is it to go ahead and construct this in the field and then measure speeds before and after a revised construction, or how do we take your model and verify its authenticity in the field?
A good next step would be to do driving simulation model and to test the effects of the deflection angle before getting the speed. I think that would be a good next step to proceed from here. Because we were able to see in microsimulation that we were able to see that there was a difference in the speed. So we got it tested with how people behave when they actually get onto the deflection angle and see if it proves and get that.
And one other point, I just want to make sure that we clarify for everybody. So I think you touched on it, but for the benefit of others, other students in particular that might be doing work that involves microsimulation where speed is a desired output. You talked about how you started with this end, but then the challenges associated with capturing actual speed. maybe just elaborate a little bit more on that if you could, in terms of why capturing speed or using speed as an output in microsimulation is a challenge.
So we'll be able to see the difference in speed on the with the turning movements. Like in a straight linear approach, there wasn't we won't be able to see a difference in speed. But as a vehicle enters an approach, there should be a decrease in speed. And in this, when I was checking out the turning movement speed of the vehicles in the first model when we started this research, the vehicle there wasn't any variance with the speed. We had to use an external factor, like use a reduced speed area, or use an external factor to reduce the speed. It wasn't a driver behavior attribute. It was more on an external parameter which you had to induce.
So in other words, it was an input,
Yes.
which, because it was an input that you ultimately controlled, you couldn't really use it as a measurable output.
Exactly. So that was the reason I had to use AIMSUN.
Excellent. I think that's something that gets lost on a lot of folks probably.
And would you like to, sorry, Dom, go ahead.
No, go.
No, I was going to ask Akshaey to clarify a little bit on the development of this scenario. So if you go back to slide 24, I think. Would you like to elaborate why this, what do you mean by equivalent sections, equivalent length sections? 24.
Okay. So what I meant by equivalent distance is, since the deflection angle is increased, the length of the approach is also increased. So to get a correct comparison, to compare apples with apples and orange to oranges, so I had to separate split the approach based on ranges. So the first split was between the first split of the approach was split into 3 distances. So we had ranges. The first section was within 45 feet. The second section was between 45 to 95 feet. And the third section was between 95 to 150 feet. So this gave us a clear comparison to compare what happened in each section and what happened. We were able to actually compare time and distance and trajectories based on it. So this is the reason I had to split into sections.
And by data points, you mean?
The trajectories at any time point.
Okay. Thank you.
So I had a question on slide 28. My question was about the number of conflicts, and then it says 1.5 seconds. Could you explain that point a little more?
Yeah, sure. So in SSM, so we had to input a constraint or a factor. So for it to for it to pick the vehicles from the trajectories. So if the distance between 2 vehicles is somewhere around 1.5 seconds, and then the SSM would consider that as an impact. So that's what this number specifies. So if the headway or if the PRT is somewhere around 1.5 seconds, it will consider a crash.
Oh, okay. I see. These are definitions. Okay.
Yeah, definitions for the SSM model.
Now I follow it. Thank you so much.
Yeah.
So I have another question. This is really interesting because I can see the benefit to pedestrians when cars slow down, and then the different angles and that the line of sight changes. But I'm wondering, do you have any thoughts on what these types of approaches might do to the flow through the traffic circle or the roundabout, which is the reason a lot of places put them in, is to keep traffic moving. Do you have any sense of whether or not we'd be giving up flow or number of cars through in a certain period of time to get the these deflection angles and the safety for the pedestrians?
So I'm sorry, but the question exactly is to if I had any example on if I have done any research based on capacity and deflection angle. Is that your exact question?
Well, my question is not necessarily if you've done research, fantastic. If you haven't, do you have any speculation about whether adding these curves to the entrances of roundabouts, which give us, you talked about pedestrian, changing the line of sight, and I imagine that increases the safety of pedestrians, but I'm asking if we're increasing the safety of pedestrians, but to do that, we're giving up flow, the number of vehicles in a certain period of time, getting through the intersection.
Yeah, I get where you yeah, I get your question now. So it's definitely gonna increase the queue because the vehicles are gonna slow down right before when they're entering the approach. So I was able to see a little increase in delays, which means there's an increase in queue. But since a roundabout will be able to operate under a capacity, I don't think there will be any problem with flow. Like until like a roundabout a roundabout will only fail as the volume hits the capacity. So until that, I don't think a deflection angle will have major impact on flow rate.
It's interesting.
No, I was gonna,
Go ahead.
yeah, so now I was gonna add that it probably depends on both the car volume and the pedestrian volumes that we will be seeing at the roundabout. So it will be a combination of the two, whether capacity will be reduced or not. But we haven't really done that part of it.
Yeah, I'm not saying it's a bad trade-off. I was just wondering because there's an intersection near here that used to be a four-way stop that had horrendous delays, at commute times, and they've put in a roundabout, and it's much faster, but the cars still back up in one direction, like going towards campus in the morning and away from campus. In the afternoon, not nearly as far. They used to back up like a mile, or at least half a mile. It felt like 5 miles. Now it's 10, 15 vehicles that I've seen, and so it's much shorter, and you do get through it much faster. And of course, the people who are going the opposite direction get through much faster. But I was just curious about that because at the same time, it's near a school, and so certain times of day, there's also probably some heavy pedestrian traffic there. And so I was just curious. I appreciate your thoughts.
Yeah, I think pedestrians is something that there hasn't been much research on, like the impact of pedestrians on capacity, or we started looking at the impact of pedestrians on emissions actually on another project we had.
And it could, and I mean, and that would actually, the emissions is much, in many ways, tied to the delay or measures that would be used to derive the delay. So I think that's something that we could actually pull out pretty nicely from some of our other work.
Yeah, and I think it's an interesting conversation to have because if you could show that you don't get you might get some reduction in the number of cars that get through, but you can increase pedestrian safety by a great deal by doing these things. I think it's a great argument for doing them. Of course, I'm for increasing pedestrian safety, even if it increases time, because cars are big and participants are comparatively small, and it's not a fair fight. Okay, well, I want to thank you all very much. I don't see any other questions coming up, and so I will. Jacob will be processing this video, and the video will be available online by the end of the week for anybody who wants to watch it again. And I think, do you have a slide with contact information? So if people want to email you with questions or just because they're interested in your work?
Yes, I've added this in the last slide.
And so, there you go. One too far. There it is. There's Akshay's contact information.
It's fine, you can call me Akshaey.
Yeah.
Awesome. It's fine.
Excellent. So thank you very much, everybody. And I hope you're all having a good Tuesday afternoon.